All right, welcome back, everybody. All right, last class we got into possibly some of the wiggiest stuff in physics. Okay, so in my opinion, some of the wiggiest stuff in physics is special relativity, Einstein's theory of special relativity, and quantum mechanics. So anytime we get a chance to touch on those in class, I get very excited. So special relativity. Here's my advertisement for special relativity. We saw last time the strange conundrum that if we had two charged particles and they were moving relative to you, so we saw that you would observe not only that these particles behaved as though there were an electric field between them because they're charged particles, but because they're moving, you would observe a magnetic field. And you would observe that these particles also respond to that magnetic field that you observe. Remember that, right? And then we sent Corey running really fast, and he was supposed to catch up with them. And so when he ran and caught up with these particles that were moving fast, he no longer observed a magnetic field. He only observed an electric field, and yet the motion needed to be the same in some sense. So both observers, both the observer sitting here in the classroom who saw the two particles go by at a particular speed, and Corey who ran to catch up with the particles and had no relative speed with respect to them, we all needed to observe that the same physics was operating, that the same physical equations applied. Okay? So as long as we did our measurements carefully, we got reasonable answers. As long as Corey did measurements correctly, he got reasonable answers. And yet, we observed a magnetic field, and he observed no magnetic field because he was running alongside the particles. And since the particles weren't moving with respect to him, there was no velocity. If there was no velocity of this charged particle, it was not putting out a magnetic field. You remember this conundrum we had at the end of class, okay? It's all due to this guy right there, Albert Einstein. You probably haven't seen this picture yet of him. It's kind of a rare photo. So this is Einstein's relativistic fitness program, okay? I call it Get Ripped with Einstein. I hope that doesn't have a meaning that I didn't know about. But anyway, get physically fit, okay? So here's the deal. If you run near the speed of light, Einstein has told us that by running near the speed of light, you can slim up your physique. Yes, it's true. And as you run faster near the speed of light, your muscle mass will increase, okay? And you will live longer, all by running near the speed of light. You ready? Observe me carefully. I used to run in college, and here's what it looks like, okay? Okay, all right. So you see that? I got skinnier, right? And I got muscle mass increased, and I just extended my life by 0.0000 something mumble seconds, okay? Because I ran, and Einstein says that'll make me live longer. So here's the physics words we put to that. The slimmer physique idea is that there's a length contraction that happens when you observe things that are moving near the speed of light. There's a mass increase that you observe as a particle moves near the speed of light, and you observe a time dilation. I'll tell you what all of that means. But the crux of it is that when you observe something that's moving fast near the speed of light, you will observe a length contraction. That the length you observe for this object contracts, gets smaller. Contraction means gets smaller in the direction along the motion. You'll observe the mass of the object increases because it's moving faster. We call that mass increase. And you'll observe what's called a time dilation. That is, that if you could read my watch as it goes by, okay? If I ran really fast and you watched what my watch was doing, and I'm watching you watching my watch do something, okay? You would see my watch slow down, according to you. According to me, it's fine. But according to you, you would say, hey, her watch is running a little bit slowly, okay? So that's what you would observe. So why is this going on? Why was this Einstein's great relativistic fitness program? All right? It's because, essentially, the speed of light is this inviolable constant, okay? So the speed of light, what we mean by the speed of light, c is what we call it, is the speed of light in vacuum, all right? Light, by the way, if light travels through materials, light can have a different speed inside of materials. The reason being light interacts with materials. It can get absorbed and re-emitted, absorbed and re-emitted, absorbed and re-emitted. All that absorption and re-emission takes time. So you might observe that a photon moving through a material slows down a little bit. That's why what we're really talking about here, c, is the speed of light in vacuum. The speed of light where it's not going to be bothered by anything. Okay? That number turns out to be an inviolable constant. Nothing can go faster than the speed of light. And it has to do with this Lorentz factor, and I'll show you how to use that. But essentially, what we're going to see is that space and time warp, kid you not, space and time warp so as to keep the speed of light this inviolable constant. So last class, we sent Corey running along to catch up with those two positively charged particles. If we had sent Corey chasing a photon, he would never catch up. Space and time would warp, okay, so that he could just never catch up, and no matter how fast he ran with respect to us, he would always measure that the photon was moving at the speed of light. We would measure the photons moving at the speed of light, and even Corey, running as fast as he runs, would still measure that the photon's moving at the speed of light. There are things that get warped by this constant called the Lorentz factor, or gamma. We use the Greek letter gamma for it. But let me at least let you get to know this gamma factor. So this is called the Lorentz factor. It's 1 over square root of 1 minus v squared over c squared. And it'll turn out that things you measure get changed by this factor. Okay? So there'll be some things that increase by a factor of gamma, some things that decrease by a factor of gamma. So let me tell you what the gamma is, and then I'll show you where it goes in the equations. So here's what that plot looks like. Basically, v is the speed of something that you're measuring with respect to you, all right? And you need to be in what's called an inertial reference frame. An inertial reference frame is just that you are moving at constant velocity. You're not changing your speed and you're not changing your direction. So if you're moving at constant velocity, then you get to be called an inertial reference frame. You are authorized to make measurements on behalf of the physics world. And then the velocities that you measure for other objects relative to you go into this equation, okay, as speed. Okay? And then you'll measure the speed of objects. And as these objects that are being measured relative to you have some velocity that approaches the speed of light, gamma blows up. Let's just look at the mathematics of this thing. So if I go back to v equals 0, okay, let's just say I'm measuring something that's in my reference frame. It's not moving with respect to me. And then I would say that, well, the speed of it is 0. 1 minus 0 is 1. And then this thing turns into 1 over square root of 1. All right, what is 1 over square root of 1? Okay, right, what is 1 over square root of 1? 1, okay. So way back here, when the velocity is 0, gamma is 1. As the velocity gets near the speed of light, this constant blows up. So let's just think about what would happen if v approached c. So if v is approaching c, this thing gets very close to 1. V squared over c squared approaches 1. I get 1 minus 1 is 0, okay? Square root of 0 is 0. So what's 1 over 0? Infinite, okay? Or the math majors are saying, it's really undefined, but what we mean is that the thing is tending towards infinity as velocity gets near the speed of light. So this thing blows up, all right? And it's always, no matter what, it's always greater than 1. Okay, so it's either at 1 or greater than 1. Your whole life, by the way, where are you on this graph? So this thing is blowing up as the speed gets near the speed of light. The speed of light in vacuum is about 3 times 10 to the 8 meters per second. I don't know if you've noticed this, but that's not on your car, right? Your car's speedometer does not have that on it. So this is really, really fast. Your whole life is not just here where it's flat. Your whole life is way back here, okay? I'm not trying to say that you're a 0. I'm just saying that you're here somewhere. I better use the laser pointer. You're there, okay? Your whole life has lived right here in a tinier spot than that pixel. Okay, so you're used to gamma being 1, okay, in your everyday life. But if you could run fast enough or observe things that were moving fast enough, this gamma starts to become appreciably different than 1, and then things get, well, kind of wiggy, okay? You'll start to notice then that space and time warp so as to preserve the speed of light. So here it is, space and time warping to preserve the speed of light c. We use this Lorentz factor, gamma. Gamma we saw from the plot is always greater than 1. So if I remind you then of Einstein's relativistic fitness program, where if something's moving near the speed of light, you get a length contraction, all right? There's a mass increase and a time dilation. So here, so the way we can then work this out is what's on the left-hand side is what you observe. So the left-hand side is what you observe for the object as it's moving quickly. The right-hand side, this L, would be the length of that object that you observed when it wasn't moving quickly. When it moves quickly, the length you observe for it is down by a factor of gamma. So now I just need to think, okay, length contraction, and I look at gamma. I know that gamma is greater than 1. So to make this equation work out so that I observe a smaller length, I need to divide by gamma, right? Gamma is greater than 1. I divide by gamma. That gave me something smaller. So the observed length is smaller. I know that the mass is going to increase. The mass that I observe will increase. How do I get the original mass? This is the mass I would observe if this particle were not moving relative to me. How do I get the mass to increase? I need to multiply by gamma. Then the observed mass has increased. Time dilation is a little bit trickier to work out, but what you're trying to get that to do is so that the time you observe going by on somebody's watch as they're running by really quickly, that slows down. So time slows down. So here, all right, so what does this look like? So I'm going to try it real quick. Ready? Einstein's relativistic fitness program. So as I run really fast near the speed of light, and try not to knock off all those mics and things like that. Did you see it? I got skinnier. Yeah? Watch again. Ready? See? Yeah. Okay. So you get a slimmer physique because you get that length contraction in the direction you're running. Also, as I ran faster, my muscles got denser, right? Everything got denser, actually, okay? So you gain mass everywhere. But hey, if I were writing this as an advertisement, I would say, hey, your muscle mass goes up. And I just extended my life by running quickly because, I don't know if you can notice here, but as I'm running by quickly, my watch is moving slower. So I just gained 0.00000 something or other 0.01 seconds on my total lifespan. So I'm going to live that much longer. So space and time warp so as to preserve the speed of light c. This is what it means for our observations. It also means that if I took a stopwatch, or it doesn't have to be a stopwatch, but any kind of watch, let me take any kind of clock and move it relative to you, you'll notice that the clock gets skinnier, it gets heavier, and it runs more slowly. So that's what all you observe. Here's kind of an interesting thing, philosophically speaking, okay? So you've heard of the theory of relativity before, I'm sure. Have you also heard of relativism? It's a philosophical idea. Okay, relativism is a kind of philosophical idea that, well, things depend on your frame of reference. So different people observe different things, and so there's one thing that I observe is not the same that you observe, so things are relative. So this idea kind of made its way into philosophy and then into pop culture as relativism, which is kind of interesting to me because the original physics is actually not about how things are relative. The original physics here is about how the speed of light is a constant. So really, this shouldn't have been called the theory of relativity, as if things are all relative. It should have been called the theory of the absolute constant of the speed of light in vacuum. It means that every observer observes the exact same thing. The speed of light is always the speed of light. So it's kind of interesting to me that that physics theory kind of got percolated out and ended up as an idea of relativism. All right, so these are the consequences for length, mass, and time. As we already saw, there's also consequences for electric and magnetic fields. So electric and magnetic fields also adjust so that the speed of light is a constant to any observer. So it's a little bit like this, okay? We saw that for those two charged particles moving by, if the two charged particles were not moving with respect to us, we only observed an electric field. But if they moved relative to us, now they have a velocity, and now they are producing from our frame of reference, we see a magnetic field. And it depended on the velocity of the particles relative to us. Here's an analogy for that, okay? When the two charged particles were not moving with respect to us, we just observed E. We said, look, they're two charged particles. They're not moving with respect to us. I observe an electric field. And yet, as those two charged particles start to move, we'll measure an electric field, and we'll also measure just a little bit of magnetic field. And the faster they move, the more magnetic field we'll see. And the faster they move, the more magnetic field we'll see, and so on. So I can make an analogy between rotating this cube between, well, are you seeing magnetic field, or are you seeing electric field? Okay? And as this object moves faster, you're going to see more and more magnetic field and more magnetic field. So it's a bit like rotating this cube. Moving at different speeds is like looking at this cube from different angles. You'll see different pieces of the electric field, different pieces of the magnetic field, depending on how fast you're moving. And so, really, it means that I shouldn't think of the electric field as a completely separate object from the magnetic field. I should think of them as a unified electromagnetic field. And as I move at different velocities relative to what I'm observing, I will see different pieces. So if I move faster, I start to see more magnetic field. If I move faster, I start to see more magnetic field. So we now call this thing a unified field, the electromagnetic field. And by moving at different velocities, you see different pieces of it. This is just an analogy, but it's an analogy I happen to like. So electric and magnetic fields look different for different observers in different reference frames. Reference frame means you're moving at a constant velocity with respect to what you're observing. Everybody can correctly predict what they observe using the exact same laws, though. Okay? So the laws of physics are the same in every reference frame. It's just that the details about, well, exactly what velocity did you measure, those are different in different reference systems. Do you have any questions about that basic idea? Okay? All right, so let me show you what the equations look like for the electric and magnetic fields. So here's a positively charged particle moving with a particular velocity with respect to us. Okay? So when the thing was sitting still, we might have observed a particular an electromagnetic field. So on the right-hand side, you've got the components of the electric field and the magnetic field that you were observing before this system started to move with respect to you. Once the system starts to move with respect to you, now I get a gamma factor, okay? And gamma is going to then rotate this cube around. So whereas you were seeing one side of things, as the system gets boosted relative to you, this is going to shift a little bit, okay? So the primed, the things over here that have a prime, the primed fields, are the new observation based on when this thing is actually moving. And things get scaled by factors of gamma coming up. And also, you'll see that magnetic fields convert into electric fields. Pieces of electric fields convert into magnetic fields because it's all one electromagnetic field, and you're just seeing different sides of it. Do you have any questions about that basic idea? Yeah?
Why doesn't it change on the x-axis for these?
Oh, you're asking a fantastic question. So he's saying, okay, I've got this moving on the x-axis. Why are these things not changing on the x-axis? I think you can think of it, and if you go back to charged particle and what's the magnetic field that I observe. So let's think about that. Let's go back to thinking of a single charged particle going by, okay, and then it's going to have a magnetic field coming out of it. So I can think in terms of the right-hand rule again of boosting this charged particle. It makes a magnetic field that is in circles around it. No matter how fast it goes, I will never observe a magnetic field parallel to its direction of motion. Yeah. The magnetic field is always, excellent question, okay? So he's pointing out that this guy didn't change. That's because along the direction of motion, the charged particle, you would observe the charged particle is creating magnetic fields that circle around it, but nothing heading towards or away its motion. Yeah, good question. Okay, all right. So that's some fun relativity. Now, back to non-relativistic. I guess I should ask, do you have any other questions about the relativistic side of things? Right? Okay, so now let's get back to using this stuff for useful things. Okay, relativity is also useful, by the way. We have to use those kind of corrections to make your GPS systems work. So we do actually make use of these things. But most of your experience in everyday life, things are not moving at relativistic speeds. So here's an example of what can happen if I have a current-carrying loop of wire in a magnetic field. I can actually use it to build up a motor. So let's think of how that might happen. So I want to think about the magnetic force that a current-carrying wire feels in a magnetic field. So here, the arrows pointing up represent magnetic field. I have a current-carrying wire, okay? Current's moving along this direction, and I have an axle. I've made the wire rectangle shaped so that I get easy pieces of the wire to calculate. So here, this is all one particular direction, and this is all one particular direction. You know, in real applications, people don't tend to use square-shaped wires. They tend to just have them whatever configuration is easiest. So if I look at this guy from the side, all right, so what I'd like to do is look at this guy from the side and think about there's an axle coming out of the board. Over here, I've got current coming out towards you, and over here, I've got current going in. But understand that the current comes out of the board, runs along a wire that I have not written down, right? And then goes back into the board, and then runs along a wire that's behind the board that I'm not drawing, okay? Current comes out towards you, runs back over here, goes back into the board. Now, how can you remember the dots and the X's? Here's let me give you a couple of mnemonic devices for remembering dots and X's. So here I have a pen that's got a point on it. Okay, when the point is pointing towards you, that's like current coming towards you. Let me try that again. Okay, so if the current's pointing towards you, okay, represented by the direction this pen is pointing, you see a point, right? So that's this guy. That's a point coming out at you. Or if I want to think of the other side where the current's reversed and the pen essentially, I can think about the pen going through the page, okay, and poking out. You kind of see how what's left is an X. This is how I remember which way it goes. Okay, so the X is like the pen already poked through. Another analogy you can use for this is to think about an arrow. So when the arrow is pointing towards you, you see the tip of the arrow. Okay, current's coming out. When the arrow is pointing away from you, it's got those little tail feathers in the back that are kind of a cross configuration. You're seeing the end of the arrow going away from you. It's just a mnemonic device to help you remember that point means it's coming towards you. X means it's going away from you. So we're seeing it from the side. All right, so now if I think about, well, what happens if I kind of tilt this thing on its axle? Okay, so I have this current loop. I'm going to tilt it on its axle. The magnetic field is an applied magnetic field. So we have some net large applied magnetic field that's going to be constant throughout all of this. And I want to think of how does the current carrying wire respond to that magnetic field. So the current loop can rotate on its axle. Maybe it's going to rotate this way. Okay. Maybe it can rotate the other direction. Okay. Okay, so let me set up the problem for you. So thinking in terms of magnetic force, where the magnetic force is I delta L cross B, so this would be the force on a current carrying wire due to an external magnetic field, so an applied magnetic field B, and then a current carrying wire. Tell me if this is the situation. So same loop of wire with an axle. So I have the axle oriented so that it's coming out towards you. The magnetic field is up. And here at the top, current is coming towards you. Then it goes down and back into the page at the bottom and then back and around. In this configuration, which of those diagrams represents the forces on the wire? Okay? You'll have to use the right-hand rule. All right, this is a tricky problem, okay? So tell me what you're thinking. Does anybody want to walk us through using the right-hand rule to get to one of these answers? Because it's not immediately obvious. You have to walk through all the steps. Anybody want to volunteer their neighbor to? Yes! All right. Oh, man. He's like, I am not sitting next to you anymore. Yeah, exactly. That's what I'm thinking.
Okay. Just use the right-hand rule. Force pointing direction.
Okay. All right. So tell me if I'm getting this right. He's saying in the top case here, that current coming out towards you. Okay. I'm going to use I delta L cross B. I point my fingers in the direction of the current, which is out towards you on the top. Rotate so that I can curl my fingers towards the magnetic field, and then my thumb points to the right. Sorry, that's my right, your left. Thumb points this direction. So one of these two must be right. And then on the bottom, the current's going back into the board. So I point my fingers in the direction of the current, curl my fingers up towards the field, and I get a force to the right. Yes, this is your right as well. So I get the force in this direction. Now, some people like to use the three fingers. And in fact, I'm not familiar with the three fingers, so I'm learning it because the 830 people make me use the three-finger rule because they always like that. So let me try, since a lot of people like that, let's do it with a three-finger rule. So here I've got current coming towards you, so index finger along current, second finger along field, and then thumb points along force. Okay? And then for the other side, you'll just reverse it, right? It goes in the other direction. Okay? Other things we need to get, did I do it right? Okay, all right. Yeah, it must be that ECE must teach the three-finger rule, because overwhelmingly the 830 section is all using this. So I had to learn it because this is what they kept telling me to use. So I learned it like this. Okay? Questions? All right, this is worth going over again. If you found this one tricky, and a lot of people did, definitely go over this tonight, okay, later. So this is the right one. It's going to be D. In this configuration, that current carrying loop is going to tend to spin. Okay? So there are some orientations then that we can put this current carrying wire in the magnetic field where it will tend to rotate. Okay? This is a good thing. This means that we can do useful stuff. In fact, so you remember we had a couple lectures ago, we talked about a bar of metal that we were going to drag through a magnetic field. Right? We had the magnetic field pointing in a direction that was perpendicular to the bar, and then we moved the bar perpendicular to the magnetic field. We saw we could drive current with it. Okay? So that means we have a way to convert electrical energy into mechanical energy. This is a way to do that, right? If this loop of wire feels forces tending to rotate it, then we're converting electrical energy into mechanical energy. Or alternatively, I also have a way to take a bar, right, and move it through a magnetic field. It'll generate a current, all right? We said if we kept moving that bar forever, hooked up to really long rails, we could drive a current as long as we wanted. Or the other easy thing to do is to just move that bar back and forth. And now I've got current running one way, and then the other way, one way and the other way, and that's oscillating current or alternating current. And so you can use either of these ideas to convert electrical energy into mechanical energy and back and forth. So we should expect then that we have ways to make a motor. So here we're going to convert electrical energy into mechanical energy. Okay. We have coils of wire here that are making magnetic fields, and then these guys in the middle are responding to the outer magnetic field. Okay. All right. It's got a pretty nice axle, so that'll keep spinning for a while even when I unhook it. So there's a way to convert electrical energy into mechanical energy. You can do the opposite. You can convert mechanical energy into electrical energy. So let's see which bulb is lighting up. Oh yeah, there you go. Okay, so here I'm using that same principle of moving wires through magnetic fields. Okay, I'm supplying the energy, but moving wires through magnetic fields in such a way that that generates currents and then can drive the bulb. All right. And what's kind of fun about this demonstration is that there's different bulbs we can try. That's an incandescent bulb. All right. We can flip this over to the big green guy, okay, which is pretty bright. And there's something up here that I need to have one of you guys come up here and try this so you can tell the class. Otherwise, I don't think you're going to believe me. So I need a volunteer to come up here and try this. Fair is fair, man. You volunteered him for the iClicker question. All right, give him a round of applause. This is hard stuff. Okay. All right. Thank you. So all I want you to do is just turn that thing and run the bulb. Okay. So what's your observation then about trying to run the two different bulbs by this method?
That one is far easier. It takes a lot less effort.
Okay.
A lot less current, I would say.
Okay. So this bulb, and they're giving, similar output. Actually, this probably is giving out more light. This one's LED, this one's incandescent, and the incandescent one's harder to run, according to you. Yes? All right. Yeah, give them a round of applause. That's all we needed. Thank you very much. Okay, so I wanted a student to try that because it was surprising to me how different it was, okay? How much harder it was to run that incandescent bulb. So if you have incandescent bulbs in your apartment or home or whatever, and you flip on a light switch, think how hard those little squirrels are working for you, okay? Whereas if you would just convert to LEDs, they could take a break once in a while, okay? So poor little squirrels, convert to LEDs. So what's going on here is that we've talked about this before, the incandescent bulbs are not very energy efficient as far as producing light. So these incandescent bulbs invented by dear old Edison, they just work by getting hot. That's all they do. You're dumping energy into heat. The filament heats up enough to where it glows, right? We've talked about this before, that everything that has a temperature glows, all right? We're all glowing in the infrared. You can't see it unless you put on IR goggles, all right? But things that get hotter glow brighter and glow at higher frequencies. This bulb gets so hot that it starts to glow in the visible. But that's its main mechanism. It's just getting hot. So this dumps tons of energy into heat, which if all you wanted was a light bulb, is not an energy efficient thing to do. This guy, for the same light output, uses 5% of the energy. You felt it, okay? So it uses about 5% of the energy for the same light output. And LEDs are light-emitting diodes, so that's sometimes you'll hear that called solid-state lighting. That's my field of physics. So my field of physics is basically about materials. We call it condensed matter physics now. Used to call it solid state, then we decided to modernize and call it condensed matter, and now nobody knows what it means anymore. But it basically means stuff you can touch. It means materials, okay? So this is my field of physics producing cool things like that. All right, so we can convert electrical energy to mechanical. We can do it the other way around. We can convert mechanical to electrical. It's all basically based on this principle of you need to have some wires that are in a magnetic field. You're either going to supply the current, okay, and then the loop of wire will turn on its own, right, and that's a motor, or you're going to supply the turning, and then you'll cause currents to run in the wire, right, and that's a generator. So let's think in this case what that looks like. So here we've got our loop of wire. The axle is coming out of the board. At the top here I've got current coming towards you. It goes back down again and then into the board at the bottom and then back up. And in all these graphs the magnetic field is up. Let's think about the forces here. So you already solved this case. You said, okay, in this case the forces are such that the axle is going to turn that direction. Let me have it in a slightly different configuration. I've still got the current coming out on the top. So current's coming out towards you on the top. And you do the same right-hand rule. The current comes out towards you. Crossed into the magnetic field going up gives you a force to the right. So this one tends to turn that direction. Way over here, okay, so this is later in time, it's rotated. And way over here, it's still got the forces in the same direction, basically, right? So current's coming out, magnetic field goes up, forces to the right. Now, one of these configurations, though, is a little bit more stable than the other. And we'll get to that in just a second. Okay? So you can think about how, all right, this guy's coming around. When it gets to this case, though, forces are pulling it out, all right? So this guy, once it goes horizontal, is really just going to tend to stick right where it is, all right? Unless I can reverse the current. So here, all right, let me show you again. And going from this slide, see how current's coming out towards you, all right? The next slide, I've reversed the current, okay? So reversing the current, reverse the forces. So now think about this original configuration. Current's coming towards you. This tends to rotate to over to here, all right? And now in this case, now when you get to this instant in time, if this went back down, it would tend to just come back to a stable equilibrium. But if when this gets down to the bottom, I can reverse the current, I'll kick it the other direction, okay? All right, and that has to do with the idea of stable and unstable equilibrium. So here, think of this configuration and think of this configuration. Both of these configurations have a net force and a net torque on the loop of wire that's 0. So in this case, magnetic field's pointing up. Here, current's coming out of the board towards you on this side. Okay, I cross B gives me a force that direction. Over here, the force is in the other direction. So it's pulling the wires in opposite directions. There's no net motion in this case, and this is stable. Okay, so if I were to tilt this thing just a little bit, it would tend to come right back to where it was. This guy, on the other hand, is also in equilibrium in the sense that there's no net force on it, but it's what's called an unstable equilibrium, because in this case, the current's going the opposite direction, and if I tilt this guy just a little bit out of the plane, then that force and this force are such that it's going to rotate the guy, okay? So in this case, it's unstable. In the other case, it's stable. This is very similar to thinking about a ball on hilly terrain. So think about a mountain followed by a valley, a mountain followed by a valley, and so forth. And let me put a ball in that landscape. Where does the ball tend to want to be? The top of a mountain or at the bottom of a valley? Where's your ball going to end up? Rolls somewhere and it lands somewhere and it stops. Yeah, it tends to end up at the bottom of the valley, okay? So at the bottom of the valley, it's in equilibrium, all right? It doesn't have a force on it one way or the other. It'll come to rest there. It's also at equilibrium at the top of a mountain, right? There's no force one way or the other. If I just place it exactly right at the top of the mountain, okay, it's balanced. But On the other hand, it's an unstable equilibrium. So if somebody comes by and sneezes or stomps their feet, or there's a little thermal fluctuation of an atom, kicks it one way or the other, the ball will roll off. All right? So unstable equilibrium, yes, it has no net force, but if there's any slight fluctuation, the thing turns. Here, stable equilibrium, if there's any slight fluctuation, it just comes back to rest. So think in terms of energy for a second. So remember this hilly landscape that the ball was rolling in, okay? Which one of those is the higher potential energy configuration? With the ball at the top of the mountain or the ball at the bottom of the valley? Which one has higher potential energy? Okay, the top guy, right, has high potential energy. And then if I let the ball go, it tends to roll down the mountain, decreasing its potential energy, and it comes to rest at a stable equilibrium. So when we see a stable equilibrium, we should think of that as lower potential energy, just like that ball in the hilly landscape. Or if I see an unstable equilibrium, I should think of that as high potential energy. Okay? So this guy has high potential energy. This guy has low potential energy. A slight deviation here, it's not going to return, right? So something happens to knock this a little bit off center, and now the forces are such that it's just going to flip. All right? But in this case, a slight deviation, well, the forces were already out, and so a slight deviation, the forces stay out and right it again back to where it had started from. Okay? Do you have any questions about that so far? Okay? All right. So if we think of the kind of situation here, if I could get this guy, so let's say that I have this guy going. In both cases, the magnetic field's pointing up, okay? So let's say I have this loop of wire and it's spinning such that it's going to get to this position, all right? And then if I had a little bit of kinetic energy to this thing so that it passed that point, so let it have just a little bit of kinetic energy so that it passes that point, okay? And then if I suddenly switch the current, if I could just go bam, flip a switch, current flips direction, all of a sudden it's going to flip over, right? And then it'll try to get to its other stable equilibrium. But if it's moving fast enough, it'll pass that equilibrium. And if I could at that instant reverse the current, it would bam, get another kick. And then it comes back to here. And then as it's passing that point, if I could switch the current, it would get another kick. So motors rely on this principle, okay? So basically, you run the current one direction and you get a torque going one way. And then as the system passes through that equilibrium point, right? Basically, you switch the current so as to turn what had been a stable equilibrium into an unstable equilibrium. Okay? So here, just as that thing goes passing the midpoint, we're going to reverse the current such that it gets a kick. And then when it's passing its midpoint again, we're going to reverse the current so it gets a kick. So a similar idea would be thinking of this ball in the hilly landscape. Okay? I get the ball up on top of the hill, I let it roll down the hill, and just as it hits the bottom, at the right time, when it's hitting the bottom and going to have a little kinetic energy to go past the equilibrium, I'm going to flip the world upside down, convert mountains into valleys and so forth, put that guy back up at the top of an unstable equilibrium and let it fall down. And then just as it gets past it again, I'm going to flip the world upside down and so forth. And I'll be able to get that ball to keep going. Same ideas here energetically. We're going to keep flipping the current. So basically, all motors are set up this way, so as the current loop gets to that spot that is going to be a stable equilibrium, you automatically set things up so that the current reverses direction. And here's a way to do that. You can think of a lot of configurations, but here's a way. So here in this case, I have the battery coming up, and there's a ring here that's split, okay? And this ring, the split ring, is connected to the axle so that as the ring rotates, so if this rotates just a little bit more, this tape here is going to hit the other side of what's called the commutator, so the other side of the split ring, which will cause current to go in the opposite direction. So you just set things up so that as your thing rotates, you flip the current, and you flip the current, and you flip the current. And that's what's happening here. You can't see it from your point of view, but there's brushes out here, okay? That's these brushes. And then there's a split ring in the middle. Okay, so that as it passes a particular point, it changes which side it's making contact with. It just automatically happens. So it's always getting a kick and always getting a kick. And, whoa. All right, so here it's switching current, switch current, switch current, switch current, switch current. And it's just set up automatically that the geometry does that. Okay, so that's the basic principle for how motors work. Do you have any questions about itself. Okay? All right. So one of the ways that we can think about that idea, we can think in terms of potential energy, as we said, right? There's hills and there's valleys and so forth. And at the top of the hill, I want to think of something as having high potential energy. And at the bottom of the hill, I want to think of it as having low potential energy. So the way to think about this in terms of potential energy is here. This is the potential energy equation that we can use to describe that, okay, a current carrying wire has a particular orientation it wants to be in the magnetic field. That's encapsulated in this equation right here in the potential energy. So think about, for example, we had these current carrying loops that were in the magnetic field and they had a particular stable equilibrium. If I have a current carrying loop, there's something called a magnetic moment associated with that, right? If I have a current carrying loop, it generates a magnetic field, so current's going this direction. This is generating a magnetic field that comes up and back and around, and it looks very much like a magnet, right? A current carrying loop of wire is an electromagnet. It generates a magnetic field, and so it's acting like a magnet. All magnets have something called a magnetic moment, which gives you a sense of how strong that dipole moment is that's being produced. So I can describe any ring of current by its dipole moment, okay? And what we saw before is that these, if I think in this case, all right, then it's like if I think of that dipole moment, there's a particular orientation that that dipole moment wants to have with respect to the field, okay? So if this is a current carrying wire, then magnetic field's coming out towards you. I would align my thumb with the magnetic field in the middle to tell you the direction of the magnetic moment, okay? And it's such that the direction of that magnetic moment then is such that you tend to either want to align the magnetic moment or flip over the magnetic moment depending on the orientation of the magnetic field. So here we encapsulate that in the potential energy equation here. The potential energy of a current carrying loop in a magnetic field is mu dot B. Okay? So that, in fact, you can see from this that you tend to lower this energy, I'm going to want those guys to align. So if I get the situation where the magnetic moment is aligned with the magnetic field, that's the lower energy configuration. Okay? So this is just to kind of help you see the connection here, that there are forces between. So here I have a current carrying wire, and I'm thinking about the forces that the current carrying wire has with respect to the magnet here. So there's a magnet here, north and south pole, and it's going to interact with this coil of wire, which is carrying current, as though they were both magnets, right? And so we can think then in terms of the forces, the net force on this current carrying wire. If I think of reaching in and grabbing the current carrying wire and trying to pull the coil to the right, the magnet tends to pull the coil to the left, okay? And I can feel that difference. So here's a way to see all that. If I have a current carrying direction going this direction, then the net magnetic field that the wire is producing, okay, is such that you can use the right-hand rule for that and follow the current, and that'll tell you the direction of the magnetic field inside. So there's a magnetic moment coming out of the center here. The magnetic moment of a circular loop of wire is just the current times the cross-sectional area. So that gives you the strength of it, okay? And the magnetic moment points in the direction of the magnetic field produced by that wire. And then there's a particular energy associated with how this magnetic moment is dotted into the magnetic field, all right? And so we saw it before that this should be a dot product, right? Because there were configurations here where this guy tended to want to be, the current carrying loop tended to want to be perpendicular to the magnetic field, okay? So it had its lowest energy configuration when the magnetic moment of the current carrying wire is aligned with the magnetic field. Or if we flipped it upside down, so this magnetic moment was anti-aligned with the magnetic field, it was a high energy situation. What's the dot product then? Okay, let's go back to this equation and think about why this makes sense. If the current carrying wire is in a plane that's parallel to the magnetic field, okay, so keep that magnetic field pointing up. The magnetic moment is this way. What's the dot product between two vectors that are at right angles?
Send me,
0, right?
actually,
Okay.
I'll just get it.
So you saw that before, okay, in that when these guys get to be sideways in this configuration, they're at a place where the energy is actually gone to 0 in that case. So there'll be one case that's low energy, one case that's high energy. In the middle, it goes back to 0 potential energy. All right. So I think we're at a good stopping point. So we're going to stop here, and I'll see you guys on Monday.